All right, guys, what we're going to be talking about here is a method that we can use to take the antiderivative of something that's a little bit more complicated, mostly when we see two things that are multiplying together when U substitution doesn't work. So kind of keep that in mind, that is what we're looking for. Now, in order to understand this, remember we had the product rule forever ago that said if we took the derivative of U times V, it was equal to U times dv dx plus V times du dx. In other words, it was first times the derivative of the second plus the second times the derivative of the first. Now, if we wanted to, and again, this is just kind of where this comes from, so if this part doesn't make 100% sense, I get it, although this one's not super difficult to understand. What we would do, or what we could do, is we could take the antiderivative of both sides. Now, if you think about this, because right now it's just a formula, but if I was to think about this, I'd be like, you know what? The antiderivative and the derivative on the left-hand side here cancel each other out. So in reality, I could say that U times V, because the integral and the derivative cancel each other out, is equal to, and we've talked about this a little bit before, that I can not necessarily multiply, but that's more or less what's happening. I can multiply, or not just multiply, but distribute the integral sign through, so I could write this as the integral of U times, I'm going to write this as dV instead of dv dx, and we'll talk about why in just a second, plus the integral of V du. Now, this next part, it makes sense that we could do this. You might be saying, well, why would I ever want to do this? If I wanted to, I could subtract the integral of V du from both sides. So I would have that that's the integral sign, uv minus the integral of V du is equal to the integral of U times dV. Now, this is our formula, and if we look at this, like it really, if you want to look at it, you could say that the integral of U times dV, and I'll explain what that means in just a second, is equal to U times V minus the integral of V times du. This is our formula for integration by parts. Now, let me explain what's going on here, okay? What this is really saying is if I have two different things that are multiplying together, two different functions that are multiplying together, where I was able to identify one as the original function and a second function as the derivative of something else, then I could convert those things into this formula over here, and I could use integration by parts. And you're probably saying, well, how would that help me ever? And as we look at a couple of examples of where we use integration by parts, you'll be like, okay, that kind of makes sense. Because right now, and here's kind of the issue, right now, when two things are multiplying together, like we have in that we've seen in a lot of integrals that we couldn't take the antiderivative of, we were just kind of stuck. What this kind of does is it allows us to sort of manipulate the equation to make it so that maybe when we get over here, we have something that we can take the antiderivative of. And again, it's a little bit complicated. The hardest part is not actually doing the problem. The hardest part is deciding what you want your U and your dV to be. So here's how we choose those. When we look for our U, we know the derivative of that. Now, we know the derivative of most functions, so that's not that big of a deal. But if I know the derivative of something, we're going to have to take the derivative of it. I'll explain why in just a second. It also helps that when we choose our U, and again, we haven't looked at examples yet, so it's kind of hard for you to just trust that this is what I'm saying. But when I take the derivative of U, usually you want to be able to use the power rule to take that derivative. In other words, whatever it is that we're looking at, we want the power of x to get smaller every time. And that'll make sense as we start looking at examples. Choosing our dv, when we look at the two functions, we have to know how to take the antiderivative of our function in order to make that be dv. If I don't know the antiderivative of the function then that you're looking at that's multiplying, you cannot choose that to be your dv in these problems. Now again, I know we haven't done an example yet, but if we use these two general guidelines, you're usually pretty good on these problems. So let's take a look at a couple of examples where these work, and as you see them a couple times, it'll make a little bit of sense. So let's again remember the formula that we have is the integral of u dv is equal to u times v minus v times du. And what I want to know is I want to know what the antiderivative of x times the cosine of x is. Well, notice I've got x and I've got cosine of x, and those are my two different functions that are multiplying together here. I need to identify one of those as u and one of those as dv. So the first question you should always ask yourself, because I'm going to need to know those two things, u, what is that, and dv, what is that, in order to use our formula. The first question you want to ask yourself is there one of those two functions that I do not know how to take the antiderivative of? If you don't know how to take the antiderivative of one of them, then that's automatically going to be your u. Because in order, and you'll see why in just a second, but when we choose our dv, I have to know the antiderivative of that. In this case, I know the antiderivative of both x and cosine of x, so that doesn't help me at all in choosing my u or my dv. The next thing you ask is, okay, if that criteria doesn't work, then when I take the derivative of either of these different functions that we're talking about, does it cause the exponent to go down in one of those two? Well, when I take the derivative of x, it becomes just 1. When I take the derivative of cosine of x, the x doesn't go away, and you'll see why that's so important in just a second. So what that means in this problem, and every one of them is different, what that means in this problem is that our x is going to be our u, and our cosine of x is going to be dv. So I identify both of those, and I just put them in. U is x, cosine of x is dv. Now, in order for us to use our equation here that we've just come up with for our integration by parts, I need to know what u is. So if I'm looking for the integral of x times the cosine of x, and I've identified my u and my dv, excuse me, I know u, just using the formula here, is going to be x. The problem is I don't know what v is. But what v stands for in these problems is the antiderivative of what we identified dv to be. So in this case, v would be the antiderivative of cosine, which is the sine of x. And you don't worry about the plus c till the very end. When we get to the very end, we'll tack that onto the end. So I look at my formula here, and I'm like, okay, I do u times v. U is x, v is the sine of x. Then we go minus, and we have that integral sign. That doesn't go away. I state v again. Notice this v in the equation is the same as the v that is inside of the integral still. So I've got v, that's sine of x. And then I'm going to multiply that by du according to the formula. Well, you've probably figured out what du is. Du is just the derivative of whatever we decided u was going to be. So in this case, the derivative of x is 1. So I multiply the sine of x by 1. And then we always just throw a dx on the very end. It's still there from the integral. Well, you look at this, you're like, okay, how did that help me? And then you think about it for a little bit longer. You're like, wait a minute. Sine of x times 1 is just the sine of x. And I know what the antiderivative of sine of x is. It's negative cosine of x. So that would make that like plus cosine of x. This x times the sine of x, that's not inside of an integral sign at all, so I don't have to do anything with that. I throw the plus c on the end, and that tells me what my antiderivative is in this case. Now, walking through it, it doesn't seem that bad, and once you identify your u and your dv correctly, these problems aren't absolutely terrible. So just be aware that they're not bad once you get the hang of identifying u and dv. So let's do another example. Okay, here's y times the ln of y. Okay, and it says dy. It's not that big of a deal. Again, our formula is u dv is equal to u times v minus the integral of v du. So I need to identify a u and a dv. My two functions here are y and the ln of y. But remember, when we're choosing u and we're choosing dv, automatically u will be something if you don't know the antiderivative of it. So in this case, I do not know the antiderivative of the ln of y. That automatically means that has to be u. So I get the ln of y here, and then dv is going to be y. So we've got our u here, we've got our dv here. Now, this is why this gets a little bit confusing, because normally when we choose our u, we want to choose something that's going to make the power, the exponent in the problem go down. So initially you might have thought, oh, u is going to be y in this problem. But it can't be y because I don't know what the antiderivative of the ln of y is. So let's go about this and see if anything works out the way that we need it to. Okay, I've got, again, the integral of y times the ln of y, dy, is equal to u, that's the ln of y, multiplied by v. Well, I know what dv is. Again, to find out what v turns out to be, I'm going to take the antiderivative of that function. So that's y squared over 2. So I've got y squared divided by 2 minus the integral of v, so again, y squared over 2, multiplied by the derivative of the ln of y, because again, I need du right here for my formula. The derivative of the ln of y is 1 over y. So I multiply those two together. The y squared and the y cancels out, which is going to happen in all these problems. They're set up so that it'll make it a lot easier on you. So I get like ln of y times y squared divided by 2 minus, notice this is now, that y squared canceled with that y, so I just have y divided by 2 dy. Well, this 2, I can move out front and make it 1/2 because we're dividing by that. And then the antiderivative of y is just y squared over 2. So I have the plus c. Then I have my ln of y times y squared divided by 2 on the outside. That turns out to be my antiderivative. And again, I know this is a little bit complicated, but hopefully you're kind of starting to see how we deal with these problems when we have two things multiplying together. Now, sometimes, again, this one starts out very similar to the last one. There's something I want to point out. Actually, I think this one works out fine. This is not the one I wanted to look at, but if you want to try this one, I'm going to pause it, then I'm going to work through it real quick, then you can check your work to see if you got the answer that you should have. So give me just 1 second. Okay, so here is the answer on how to do this one. Again, I chose my u as the ln of x like we did last time, and dv was x to the third. Then we just work through this, noticing that x to the fourth over 4 multiplied by 1 over x, we do get one of the x's to cancel out, and then the exact same thing happens, okay? And I got my answer down here as the answer that we normally get, okay? So there is your antiderivative there. Now you might be asking, well, how does that change when we have like a definite integral? Well, really the only difference is you need to find the antiderivative all the way, and then once you do that, then you plug in the top number and plug in the bottom number and subtract them. There's one thing I actually want to focus on this problem, and it's not the definite integral part. It's the fact that in this case, I'm going to let u equal x to the third, and I'm going to let dv equal cosine of 2x. Now, I'm not going to work all the way through this problem, so it would actually take forever, and you'll see why in just a second. I need du and I need v. The antiderivative of cosine of 2x is the sine of 2x divided by 2. So what I have here as my antiderivative is x to the third multiplied by the sine of 2x over 2 minus, then we've got v, so that is still the sine of 2x divided by 2 multiplied by, let's see, du, so that's multiplied by 3x squared. Now you'll notice in this problem that we have an issue, okay? I still don't know how to take the antiderivative of that part. So the one thing that you can do when it comes to u substitution is you can do it a second time in the problem, no worries. So on my second iteration here, I mean, I can pull the 3/2 out front because those are both constant numbers. So I've got a 3/2 here. Then now I'm going to let u equal x squared, and I'm going to let dv equal the sine of 2x on my second go-around for this antiderivative right here. So I'd have du is equal to 2x, and then I'd have v is equal to negative cosine of 2x divided by 2. I would have as my answer, and I'm still not done yet, and I'm going to stop here in just a second because I'm going to run out of screen. But I've got minus, I've got the 3/2 here, and then this. If I take this antiderivative, I'm going to have u times v, so I'm going to have x squared times negative cosine of 2x divided by 2 minus v, negative cosine of 2x divided by 2 times du, which is 2x. The 2's will cancel out. But you'll notice, and it sucks, but you'll notice that there's yet another time that we would have to use integration by parts. So you can use it as many times as you want in the problem until the integral becomes something that you can actually take the antiderivative of. So we would have yet another subtract all of this stuff down here once we use the integration by parts. And you would find that after we've done it 3 times that it finally becomes something that you can take the antiderivative of. Once we find that antiderivative, we would just plug in pi halves everywhere we see x. We'd plug in 0 everywhere we see x. And from there, we would say, all right, now that I've got those 2 numbers, I would subtract them and find out what that value actually is. Usually on the AP exam, if it's a definite integral like this one, it's not nearly that difficult to try and evaluate. Like if it's an integration by parts problem, it'll be like 1 step is all, not like 3 steps here where you'd have to plug in pi halves and 0 900 times. So hopefully that makes sense on integration by parts. More than anything else on integration by parts, it's just practice that will help you determine what your U and your dV are going to be. If you have any other questions about that, please let me know.